Welcome to this coding tutorial. In today's session, we'll be tackling LeetCode problem number 343, titled Integer Break. This problem challenges us to divide a given integer into the sum of multiple positive integers to maximize their product. It's a fascinating problem that combines mathematics and dynamic programming concepts. Let's dive in. In this problem, you're given an integer n, and the goal is to break it into the sum of k positive integers, where k is at least 2. The objective is to maximize the product of these integers and then return the maximum product you can achieve. For example, if n is 2, the only way to split it into two positive integers is 1 plus 1, which gives a product of 1. The input will always be an integer n, where n ranges between 2 and 58, inclusive. The output is also an integer, representing the maximum product from breaking n into the sum of at least two integers. Now, let's dive into some examples to understand the problem better. For n equals 2, as we just mentioned, the only possible partition is 1 plus 1, and their product is 1 times 1, which equals 1. For n equals 10, we can break it into 3 plus 3 plus 4. The product of these numbers is 3 times 3 times 4, which equals 36. This is the maximum product you can achieve for n equals 10. The key is to find the right combination of integers that yields the highest product while still satisfying the condition that their sum equals n. For another example, if n equals 8, one optimal way to break it is 3 plus 3 plus 2. The product of these numbers is 3 times 3 times 2, which equals 18, and that's the maximum product for this input. When solving this problem, it's important to also consider the constraints. The value of n ranges from 2 to 58, and you must split n into at least two positive integers. Additionally, the sum of the integers in your partition must equal n. Edge cases include the smallest possible n, such as 2, where the only valid partition is 1 plus 1, and larger inputs like 58, where maximizing the product may require applying mathematical insights or efficient algorithms like dynamic programming to handle the calculations effectively. To solve the integer break problem, the task is to split a given integer n into the sum of at least two positive integers such that their product is maximized. One potential approach is brute force. The intuition here is straightforward. We try every possible way to partition the number n into k parts, calculate the product for each partition, and track the maximum value. This method involves using recursion to explore all possible partitions of n. The time complexity is exponential, as the number of partitions grows combinatorially with n. Additionally, the space complexity is O(n), due to the recursion stack. While conceptually simple, this approach is impractical for larger values of n because of the sheer number of possibilities to explore. It is inefficient and not suitable for competitive programming scenarios. A more practical solution involves dynamic programming. Here, the problem is broken into smaller subproblems. The idea is to calculate the maximum product of integers that sum to each value from 1 to n, leveraging the results of smaller values to build up the solution. We define dp, I, as the maximum product we can obtain by breaking the integer I into at least two parts. For any given I, we iterate through all possible first numbers in the partition, say j, and compute the maximum product using two options, either splitting the remainder further, or taking it as is. This is done using the formula max, j asterisk, I j, j asterisk dp, I j. We then update dp, I, with the maximum value obtained. Finally, we return dp, n. The time complexity here is O(n) squared, because for each I we iterate through roughly n/2 possible partitions, and the space complexity is O(n) for the dp array. Although far more efficient than brute force, this approach can still be slow for very large values of n. A more optimal solution is derived from mathematical insights. The key observation is that the number 3 is the most productive number for maximizing the product when breaking n into parts. By splitting n into as many 3s as possible, we can achieve the highest product. There are a few special cases to handle. If n leaves a remainder of 1 when divided by 3, it's better to use 1 2 instead of 2 1s, as 2 is greater than 1 multiplied by 1. If the remainder is 2, we include that remainder as a single 2. The method is simple. If n is less than or equal to 3, we return n1 to ensure there are at least two parts. For larger values, we divide n by 3. If it divides evenly, the result is 3 raised to the power of n divided by 3. If the remainder is 1, we subtract 1 3 and multiply by 4. If the remainder is 2, we simply multiply by 2. This approach has a constant time and space complexity, O(1), making it extremely efficient. However, it relies on understanding these mathematical properties, which might not be immediately intuitive. Given the efficiency and elegance of the mathematical optimization approach, it is the ideal strategy for solving this problem. Its constant time and space complexity outperform both the brute force and dynamic programming methods. The crucial insight that splitting n into as many threes as possible yields the highest product, combined with the special handling of remainders, leads to a highly optimized solution. While dynamic programming is easier to generalize and implement, it introduces unnecessary computational overhead for this specific problem. The brute force method, although useful for understanding and validating the problem, is impractical due to its exponential time complexity. The mathematical approach not only eliminates unnecessary computation but also aligns with the principle that balanced and close to equal integers produce the best product. Each approach comes with its own trade-offs. The brute force method is conceptually straightforward but computationally prohibitive, making it unsuitable for large inputs. Dynamic programming is a step up in efficiency and provides a systematic way to solve the problem, yet it still falls short compared to the mathematical approach because of its quadratic time complexity. The mathematical optimization approach, on the other hand, is both the fastest and most elegant solution, requiring only a few arithmetic operations. The key insights, such as prioritizing the number 3 and carefully handling remainders, make this approach stand out. While it demands a deeper understanding of the problem's mathematical structure, its simplicity and efficiency make it the best choice for this problem, striking the perfect balance between theory and practical implementation. The integer break problem asks us to split a given number, n, into the sum of at least two positive integers such that their product is maximized. For instance, if n equals 10, the best split is 3, 3, and 4, giving a product of 36. To solve this, we rely on mathematical insights combined with dynamic programming. First, let's understand the constraints. The number must be split into at least two integers. For example, splitting n equals 2 results in 1 plus 1, with a product of 1. For larger numbers like n equals 10, we evaluate all possible combinations such as 1 plus 9, 2 plus 8, 3 plus 7, and so on. However, there's a key mathematical insight. The product grows faster when we use the number 3 as much as possible. For example, splitting 10 into 3 plus 4 gives a product of 36, which is greater than splitting it into 2 plus 2 plus 2 plus 2 plus 2, which results in just 32. This insight forms the foundation of our approach. If, after splitting into as many 3s as possible, there's a remainder of 1, such as splitting 10 into 3 plus 1, it's better to replace that 1 with a 4, as 3 plus 4 yields a higher product. Now, let's look at the base cases. For n equals 2, the only valid split is 1 plus 1, giving a product of 1. For n equals 3, the split is 1 plus 2, with a product of 2. These base cases initialize our dynamic programming array. Next, we define dp, I, as the maximum product obtainable by splitting the number I. To compute this, for each integer I from 2 to n, we iterate through all possible splits j. The product is either j multiplied by ij, if we don't further split ij, or j multiplied by dp ij, if we do. This ensures that we consider both direct splits and recursive splits. Finally, the maximum product for n will be stored in dp n. We implement this by initializing a dp array of size n plus 1, setting dp 0 and dp 1 to 0 since no product is possible for numbers less than 2. For each number I from 2 to n, we iterate through all possible splits j from 1 to I1. For each split, we calculate the product and update dp I with the maximum value obtained. Once all iterations are complete, we return dp n as our result. There are some key insights to note. First, splitting numbers into as many 3s as possible maximizes the product because the mathematical property of 3s outperforms other splits. For example, 3 times 3 is greater than 2 times 2 times 2. Second, dynamic programming ensures efficiency by reusing previously computed results. And finally, edge cases like n equals 2 or 3 require special handling because they cannot be split into 3s. For numbers less than 4, we can directly return n1 as the result. Analyzing the time and space complexity, the approach uses a nested loop structure. For each I from 2 to n, we iterate over all possible splits j, resulting in a time complexity of O, n squared. Space complexity is O, n, as we use a dp array of size n plus 1. Let's look at the pseudocode. We define a function integer underscore break. If n is less than or equal to 3, we return n1 directly. We initialize a dp array of size n plus 1, with base cases dp 1 equals 0, dp 2 equals 1, and dp 3 equals 2. For each I from 4 to n, we iterate through all j from 1 to I1, updating dp I with the maximum of the current value j times ij, or j times dp ij. At the end, we return dp n as the result. This ensures that we calculate the maximum product efficiently for all numbers up to n. For very large values of n, we can optimize the solution further by leveraging the mathematical insights directly. Instead of using dynamic programming, we determine the product based on the value of n modulo 3. If n is divisible by 3, the product is simply 3 raised to the power of n divided by 3. If there's a remainder of 1, we subtract one group of 3 and replace it with a 4, yielding a product of 3 raised to the power of n divided by 3 minus 1, multiplied by 4. If the remainder is 2, we multiply 3 raised to the power of n divided by 3 by 2. This approach eliminates the need for a dp array and is highly efficient, especially for large inputs. With this mathematical optimization, we achieve the same result with significantly reduced computational overhead. This Python implementation solves LeetCode problem number 343 integer break using dynamic programming. The goal is to maximize the product of integers that sum up to a given number n. Let's break down the code step by step. 1. The function integer break starts by handling special cases where n is 2 or 3. For these small numbers, the maximum product is n1, e.g., for n equals 2, the product is 1, for n equals 3, the product is 2. 2. We initialize a dynamic programming, dp, array dp of size n plus 1. Here, dp, I, represents the maximum product obtainable by breaking the number I. The array is filled with zeros initially, and we set dp 1 to 1 as the base case. 3. The outer loop iterates from 2 to n, representing the current number being broken. 4. The inner loop iterates from 1 to I1, where j is the first part of the split. For each split, we calculate 3 possible products. J asterisk ij, the product when I is split into j and ij without further breaking. J asterisk dp ij, the product when j remains as is, but ij is broken further using the pre-computed dp value. The maximum of the above is stored in dp I. 5. Finally, dp n contains the maximum product for the given number n, which is returned as the result. This solution has a time complexity of O, n squared, due to the nested loops, and it efficiently computes the result for all valid inputs. The use of dynamic programming ensures that subproblems are solved optimally, and their results are reused to build the solution for larger numbers. This is the Java implementation for LeetCode problem number 343, integer break. The logic directly mirrors the Python solution, using dynamic programming to compute the maximum product of integer partitions. Key differences include Java-specific syntax, such as type declarations, the math.max method for comparisons, and explicit array initialization for the dp table. The problem integer break challenges us to maximize the product of integers obtained by breaking a given number n into at least 2 positive parts. To solve this, we use dynamic programming, where we iteratively compute the maximum product for every integer up to n. The idea is to consider splitting the number I into 2 parts, j and ij, and evaluate all possible values of j. For instance, if n is 5, we start by initializing a dp array of size n plus 1 with all elements set to 0. The base case is dp 1 equals 1, since the maximum product for 1 is itself. At the start, the array looks like this: 0, 1, 0, 0, 0, 0. Then, we begin iterating from I equals 2 all the way to n. For I equals 2, there is only one valid split, j equals 1. We calculate the maximum product using the formula max, dp, I, j asterisk, ij, j asterisk dp, ij. For this split, the maximum product is 1, so we update dp 2 to 1, and the array becomes 0, 1, 1, 0, 0, 0. Next, we move to I equals 3. Here, we try all possible splits of I by iterating over j from 1 to 2. For j equals 1, we compute max dp 3 1 times open parenthesis 3 minus 1 close parenthesis 1 asterisk dp 3 to 1, which gives a result of 2. Similarly, for j equals 2, the calculation results in a maximum product of 2. Thus, dp 3 is updated to 2, and the array becomes 0, 1, 1, 2, 0, 0. Now, for I equals 4, we consider splits with j ranging from 1 to 3. For j equals 1, the maximum product is 3. For j equals 2, splitting the number yields a maximum product of 4, and for j equals 3, the maximum product remains 4. Therefore, dp 4 is updated to 4, and the dp array is updated to 0, 1, 1, 2, 4, 0. This process ensures that dp I always holds the maximum product for the integer I. Now, for I equals 5, we iterate over j from 1 to 4 to evaluate all possible splits. For j equals 1, the maximum product is 4. For j equals 2, splitting the number gives a maximum product of 6. Similarly, for j equals 3, the calculation results in a maximum product of 6, and for j equals 4, the value remains 6. Therefore, we update dp 5 to 6, resulting in the final dp array 0, 1, 1, 2, 4, 6. After completing the computation, the maximum product for n equals 5 is stored in dp 5, which is 6. This value is returned as the result. By iteratively breaking down each integer and using the results of previous computations, we efficiently find the solution to the problem. For a larger example, let's consider n equals 10. We start by initializing a dp array of size n plus 1, with dp 1 set to 1. As we iterate from I equals 2 to I equals 10, we compute the maximum product for each I by testing splits with all possible values of j. For example, at I equals 6, the maximum product comes from the split 3 plus 3, giving dp 6 equals 9. For I equals 7, the optimal split is 3 plus 4, resulting in dp 7 equals 12. Similarly, for I equals 8, the best split is 3 plus 5, yielding dp 8 equals 18. At I equals 9, splitting into 3 plus 6 gives the maximum product of 27, and finally, for I equals 10, the split 3 plus 7 produces the result of 36. By the end of the computation, the dp array allows us to quickly retrieve the maximum product for n equals 10, which is dp 10 equals 36. For smaller values of n, such as n equals 2, we handle this as a special case. Since n must be split into at least 2 parts, the maximum product is simply n1. In this case, the result is 1. This avoids unnecessary dp computation for very small values of n. The key observations for this solution are that the dp formula relies on splitting the integer into 2 parts, j and ij, and recursively using dp ij to account for further splits. For values of n less than or equal to 3, we directly return n1, as these cases are straightforward and do not require dynamic programming. These optimizations make the solution both efficient and elegant. To analyze the time complexity of our solution, we start by examining the nested loops in the integer break function. The outer loop runs from 2 to n, which means it executes n1 times. For each iteration of the outer loop, the inner loop iterates from 1 to I1. This means the number of iterations for the inner loop increases as I increases. For I equals 2, the inner loop runs once, for I equals 3, it runs twice, and so on, until I equals n, where it runs n1 times. The total number of iterations across all these inner loops forms an arithmetic series, 1 plus 2 plus 3 plus n1. Using the formula for the sum of an arithmetic series, we calculate this as en1 asterisk n/2, which simplifies to O n squared. This explains why the overall time complexity of the algorithm is quadratic. Within the inner loop, we perform operations such as the max function and multiplications like j asterisk ij and j asterisk dp ij. Each of these operations is constant time, or O1. Therefore, the total cost of the inner loop is directly proportional to the number of iterations it executes. When we combine the behavior of the two loops, the quadratic growth of the arithmetic series dominates, so the total time complexity remains n squared. Now, moving on to space complexity, the solution uses a dynamic programming array dp of size n plus 1. This array stores the maximum product for integers from 1 to n, requiring n space. Beyond the dp array, the algorithm uses only a few auxiliary variables like I and j, which take constant space, or 1. As a result, the overall space complexity is determined by the dp array, making it n. When we compare this dynamic programming approach to a brute force solution, the efficiency becomes clear. A brute force method would recursively explore all possible ways to split n into integers and calculate the product of each combination. For example, breaking n into a_1 plus a_2 plus a_k and evaluating a_1 asterisk a_2 asterisk a_k would require exploring all partitions of n. This process grows exponentially, resulting in a time complexity of 2 to the power of n. On the other hand, dynamic programming reduces this by reusing intermediate results, achieving a time complexity of n squared. Additionally, there is an optimized mathematical approach based on the property that the product is maximized when integers are close to 3. Using this property, the problem can be solved in log n time by repeatedly dividing n into parts of 3 and managing the remainder. To summarize, the dynamic programming solution offers a significant improvement over brute force, reducing an exponential problem to quadratic time. Further optimization with mathematical reasoning can bring the time complexity down to logarithmic levels, with space complexity remaining n. When solving the integer break problem, there are a few common mistakes to watch out for. One frequent error is misunderstanding the mathematical reasoning behind the greedy approach. Many assume that splitting a number evenly will always yield the best result, but that's not the case. For example, breaking 10 into 2 5s gives a product of 25, but splitting it into 3, 3, and 4 results in a larger product, 36. This happens because the optimal approach is to split the number into as many 3s as possible, except when the remainder after dividing by 3 is 1 or 2. Another mistake is overcomplicating the dynamic programming solution. Some try to compute every possible split recursively, which leads to exponential time complexity. The correct approach is to use dynamic programming to store intermediate results, reducing the complexity to n squared. Finally, there's the issue of failing to handle small values of n, like 2 or 3. These cases need special handling because the general strategy doesn't apply. For example, n equals 2 should directly return 1, and n equals 3 should return 2. Base cases ensure these small inputs are handled correctly and prevent errors in the final solution. Another mistake to avoid involves optimizing calculations when splitting into 3s. Some solutions recompute powers of 3 repeatedly, which is inefficient. Instead, modular arithmetic or pre-computing these values can simplify the logic and improve overall performance. Additionally, it's critical to enforce the constraint that the number must always be split into at least 2 integers. Some solutions neglect this and fail to handle cases where the split results in fewer than 2 parts, violating the problem's requirements. To fix this, ensure that the algorithm explicitly checks that k, the number of parts, is at least 2. These optimizations not only make the solution more efficient but also ensure correctness across all edge cases. Now, let's discuss some key insights that are helpful in an interview setting. First, a critical mathematical observation is that splitting the number into as many 3s as possible typically maximizes the product. If the remainder after dividing by 3 is 1, it's better to adjust by taking 1 less 3 and replacing it with a 4, as seen in examples like 10 splitting into 3, 3, and 4. While the greedy approach is the most efficient, being able to explain why it works is important. You should highlight that 3 consistently provides the highest product compared to any other base split. Dynamic programming, while slower than greedy, is another valuable approach to demonstrate. It shows a deep understanding of optimization and the trade-offs between time and space complexity. Lastly, interviewers may test your handling of edge cases. Be ready to explain how your solution works for small inputs, like n equals 2 or 3, and how it adheres to constraints like splitting into at least 2 parts. For extra preparation, you can explore related problems like LeetCode 279, which which focuses on decomposing numbers into perfect squares, or LeetCode 91, which uses dynamic programming for string splits. These problems share conceptual similarities and can complement your understanding. Finally, let's review some alternative approaches to solving the problem. The greedy approach is the most efficient, with a complexity of O log n. It's optimal for large values of n, but it does require you to justify its correctness through mathematical reasoning. On the other hand, the dynamic programming approach, while less efficient at O n squared, is more intuitive, especially for smaller inputs. It allows you to systematically compute the optimal product by storing intermediate results. For completeness, there's also recursive backtracking, which explores all possible splits. While its exponential time complexity makes it impractical for larger inputs, it can serve as a useful baseline or a starting point for understanding the problem. To make recursive backtracking viable, memoization can be added to reduce redundant computations. Each of these approaches has its strengths and weaknesses, and understanding when to apply them can help you tackle a variety of problems effectively. Thanks for sticking with us through this session. To wrap up, we explored how to solve the integer break problem using efficient strategies like dynamic programming and mathematical insights. We highlighted the importance of using numbers close to 3 for the breakdown to achieve an optimal product. If you enjoyed this tutorial, please like and subscribe for more helpful lessons. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!